Good morning, everyone.
Good morning.
Good morning.
Good morning.
Good morning.
Okay, so we're just getting everybody logged in here. All right. Okay, well, welcome back, everyone. I hope you had a nice weekend. Sunday was a little bit ugly for us with the weather, but certainly Saturday, Monday were pretty nice. So I hope you had some time to enjoy life a little bit. And I hope that you and your families continue to be safe. All right, so we're going to jump right into chapter 2 here today. Chapter 2 is the chemistry chapter. We have 3 lectures scheduled for this chapter, lots to do. So I'm going to get started. And of course, later today, we also have lab. So, okay, let's begin. I'm going to share my screen with you. Okay, and there we go. Again, I wish I had like a 50-inch computer monitor. Okay. All right, folks. So chapter 2 it is. Chapter 2 is the chemistry chapter. And, truth be told, this tends to be a chapter that is really not a favorite of students. Students can appreciate what the heart is, what the liver is, what a bone is. But, quite frequently, it's been a very long time since anyone's asked you to think about atoms or even electrons or things like this. So, if this conversation is uncomfortable for you, please know that that's entirely normal and that you are not alone with that, okay? All right, so let's start with a couple quick definitions. Okay, chemistry. Okay, chemistry is the science of matter. That doesn't mean too much unless you know what we mean by matter, okay? I mean, we could define chemistry a number of different ways, but I'd like to just give a starting point for the conversation. So matter, when we say matter, we're talking about anything made of atoms, okay? So the computer keyboard that you may be typing on right now is certainly made of atoms. The pen and pencils you're holding, the paper you're writing on is made of atoms. The chair you're sitting on is made of atoms. The hair on your head is made of atoms. Your fingernails is made of atoms, right? The wristwatch on your wrist is made of atoms. The air inside your lungs is made of gas molecules, which themselves are made of atoms, right? So everything that's not made of energy is made of atoms. Chemistry is the science of matter. Matter is anything made of atoms. Okay. So let's talk about atoms a little bit. Okay. Atoms are the building blocks of matter. And by building blocks, kind of the analogy that I use is that atoms are sort of the Lego bricks of the universe. And by that, I mean, maybe you have some Lego bricks at your house that your children play with to build a toy skyscraper or a castle or a dollhouse or a robot, And so what happens, right? You take the Lego bricks, you link them together in different arrangements, in different patterns, and you build an object like a house, okay? Atoms are the Lego bricks of the universe, okay? You can put atoms together, you can link them with chemical bonds, and we build larger and larger structures, okay? Typically, we don't give any thought to this, in our daily lives, we don't think about it. We just interact with matter without really thinking about what's there. Of course, when you're a scientist or engineer, you spend quite a bit of time thinking about what matter is really made of and how it has unique properties based on its arrangement of atoms. Please stop me along the way if you have questions, okay? I want you to understand, so please ask questions along the way if something's bothering you. Let's talk a little bit about atomic structure. Okay. Right, so, it's not what I wanted. Okay. And here we'll say that we started with basic definitions. Okay. All right. So, this is not a physics course. If it were a physics course, we could go into really intimate detail about atomic structure. We're not going to do that, but we're going to go to the same level of information that your textbook uses, which is to say on page 31 of your textbook, figure 2.1, you see the basic representation of an atom. Okay, now the representation you see in figure 2.1 is about 100 years old, right? This representation of what an atom is, what it looks like, is basically over 100 years old. The original model that you see in figure 2.1 was developed by a man by the name of Bohr, B-O-H-R, B-O-H-R. This is the Bohr model of an atom. Truth be told, that modern chemistry doesn't really use this representation of an atom anymore. It uses a representation based on an idea called quantum mechanics. But you know what? To understand quantum mechanics, you really need to understand calculus. And so that's why we don't start there, because most of our students have not had calculus, okay? So we're just giving you a framework to begin thinking about these topics. For some of you, you will never have to think about this again. For others, you might, depending on the path that your career takes you, okay? So please, I want to encourage you to, I will be asking some questions of you in the audience during class today. I want to encourage you, if you don't already, to please have your textbook open or at least up on your computer screen that you can reference it when I need you to, okay? That's something you should do for every lecture, is have your textbook accessible.
Mr.
Okay.
Allen,
Yes.
what page are we on again?
Page 31, figure 2.1.
Thank you.
Okay. So when we talk atomic structure, we basically talk about 3 subatomic particles. And they are as follows, right? You've heard of this before. There are protons. Protons are positively charged, and they are found in the nucleus of the atom. They're positively charged, found in the nucleus of the atom. We have neutrons, which have no charge. In fact, we would consider them to be neutral. They just have no charge. These are also found in the nucleus of the atom. And you can see, the nucleus as sort of this center of the atom model. In figure 2.1 there, we see the red and blue balls in the center. And then we have electrons. Electrons have a negative charge, and electrons are found outside the nucleus. They actually orbit the nucleus in the same way that our Earth orbits the sun. Okay, so, a physicist could go into even greater detail. Protons and electrons are made of even more primitive particles called quarks and other exotic pieces of matter. We don't need to talk about that in our biology course, but nonetheless, science is interested in these questions. Okay, so let's see what we can do here. Okay. Next talking point, characteristics of atoms. Okay, number 1. All right, so here's a question for the general audience, and I'll put it in the chat window here. what characteristic of atoms is used to identify atoms? Now, surely if you're into chapter 2 reading at this point, you should have come across some terminology that is used to identify the atoms. Thank you, Shay, for your response. Anybody else? What characteristic of atoms is used to identify atoms? All right, let me say that the answer to my question is on page 32. The answer to my question is on page 32. What characteristic of atoms is used to identify atoms? Anybody? Okay, so just taking a look at some of the responses, right? We do have a variety of responses, and they're starting to come through here. And some of your answers are different than others. That means there's disagreement. Okay, so the answer to the question is atomic number. Atomic number. Okay. Okay, atomic number is the number of protons present in the nucleus of an atom. Number of protons present in the nucleus of an atom. Okay, what is significant about this is that atomic number is the characteristic used by chemists to identify atoms. In other words, atomic number is used by human beings to tell one kind of atom from another kind of atom, right? Think about it. If you go to the zoo, right? If you go to the zoo, you can tell a tiger apart from a bear, apart from an eagle, apart from a pink flamingo, because all of these different animals have a different shape, different size, different coloration, they make different noises. It's very easy to tell different animals apart at the zoo. But when it comes to atoms, they are so small that we can't look at them, we can't hear them, we can't smell them. Okay, so it's a lot harder to tell them apart. If I had a carbon atom in my left hand and a nitrogen atom in my right hand, how would I know that they're in fact different types of atoms? And the answer is, well, if I had the right equipment, the right technology, I could measure the number of protons in the nucleus of each atom, and I would find that they in fact would be different if they are two different kinds of atoms. Okay, so atomic number is the characteristic used by scientists to identify different types of atoms. Okay, your textbook, at least in chapter 2, does not give you a periodic table of elements, but maybe you remember the periodic table of elements from chemistry class in high school if you had that years ago. And the periodic table of elements lists out all the different types of atoms known to exist in our universe. And what you will find if you look at a periodic table of elements is that no two elements on the periodic table have the same atomic number. Okay, let's take a look at this. Page 32 of your textbook, figure 2.2. You notice that there are 8 atoms listed, 8 atoms. And if you look at the information underneath each atom, you'll notice that one piece of information provided is the atomic number. And you notice that none of the 8 atoms have the same atomic number, right? Hydrogen's atomic number is 1, carbon is 6, nitrogen is 7, so on and so forth. Each unique type of atom has a unique atomic number. Okay. All right. So the atomic number basically conveys the identity of the atom so that we can tell different types of atoms apart. All right. So let me just ask a question here of someone in the audience. Just want to be sure that you folks are coming along for the ride, so to speak. All right. Let's see here. Let me find somebody in the audience that, okay, how about Israel Cologne. Israel, can you please unmute your microphone and say hi to us?
Hello,
Hi, Israel. Good morning to you.
good morning.
Israel, do you have your textbook available?
Yeah, I was trying to open it.
Okay. Can you get to page 32 in your textbook, figure 2.2? Israel, do you have it open?
Yeah, I'm having it open. I just can't figure out which page.
Okay, it's page 32, figure 2.2. Okay.
It's just,
Do you have it, Israel?
taking forever.
Okay, Israel, I'm going to move on because lots
Okay.
of time that I need to move on, so I'll come back to you. Okay. Karen Anderson. Karen, can you please say hi to us?
Hi.
Karen, good morning, Karen. Karen, do you have your textbook open?
I do.
Okay, so Karen, on page 32, figure 2.2, can you please tell me what the atomic number of an iodine atom is?
53.
Okay, thank you. So I have one more question for you, Karen. Karen, can you please tell me the number of protons in the nucleus of an iodine atom?
Hold on a second. Ooh, is it the same?
So what are you telling me? What would the number of protons be?
Hold on a second. I'm going to go with 53.
Okay, thank you, Karen. I appreciate that. You're absolutely right. And my point here is that I just asked you for the same information two different ways, right? First, I asked you what is the atomic number of iodine. Secondly, I asked you how many protons are present. That's the same question, and it's important that you realize that, okay? So how many different protons are present in the nucleus of an iodine atom? 53, okay? So these two questions are the same. Okay. Folks, do you have any thoughts or questions? All right, let's continue here. Characteristics of atoms. So we've talked about atomic number. There's other characteristics that you need to be aware of. And I'll present it this way, okay? We'll do mass number. Okay. Mass number is also something that you see presented on figure 2.2, page 32. And so here's what mass number is. Mass number is the number of protons plus neutrons present in the nucleus of a single individual atom. The number of protons plus neutrons present in the nucleus of a single individual atom, okay? And so you can see that the mass number of iodine on page 32 is in fact 127, okay? Now, why am I picking out these specific atoms? Because they are accessible to you in your textbook on page 32. Okay. Now, there's a slightly related concept, another term that's very related to mass number, and this is atomic mass. Okay, so we need to spend some time picking this apart. Atomic mass is the average number of protons plus neutrons present in the nuclei of a group of atoms. Okay, the average number of protons plus neutrons present in the nuclei of a group of atoms. Okay, so let's see how you folks are doing here. All right. Okay, let's see here. All right, hold on a sec. Okay, so let's see. Shay Davis. Shay, could you please unmute your microphone and say hi to us?
Good morning.
Morning, Shay. So Shay, I have a question for you here. First off, do you have access to your textbook at this time?
Yes.
Okay, great. So Shay, on figure 2.2, what is the mass number of a carbon atom?
Mass number is 12 or 13.
Okay, so that's what I want to pick on a little bit with you. Okay, and I'm going to come up here in my notes underneath mass number. What is the mass number of carbon atoms? And you said 12 or 13. Okay,
Yes.
so that's correct. So Shay, what does it mean that there are two numbers reported for mass number? I mean, if one carbon atom is next to another carbon atom and they're both carbon atoms, shouldn't they be the same? So the fact that I have two different mass numbers reported for carbon atoms is suggesting the presence of what?
Transference. I know that's not the term, but I remember something vaguely from chemistry before about protons and neutrons and electrons and borrowing of one and one moving over at certain points in time. I can't remember exactly, but I remember something like that.
Okay, I appreciate that you're thinking about your chemistry background. That is not important for our current question, but I appreciate your attempt, I really do. So we'll open this question up to the broader community. Thank you, Shay. All right, so here's the question that I'm typing into your document. Since two numbers are reported as correct mass numbers for carbon atoms, this suggests the presence of what? Fill in the blank for me, folks. What am I hinting at? Okay, I'm looking at the chat window here. Okay, Austin was first to respond, and he gave a correct answer. Raquel, good job. Okay, I'm talking about the presence of isotopes. Okay, isotopes. All right, so that's what I'm fishing for here. Okay, so we need to talk about this. Okay, here's a question next. What are isotopes? Okay, isotopes are atoms that have the same atomic number, but have different numbers of neutrons present in their nuclei. Okay, isotopes are atoms that have the same atomic number, but have different numbers of neutrons present in their nuclei. Think about it this way, as an analogy, okay? The phrase ice cream, okay? Ice cream is ice cream is ice cream. But think about it, when you go to the ice cream shop, the ice cream creamery, the parlor, okay, you could get chocolate ice cream, you could get strawberry ice cream, you could get mint chocolate chip ice cream, coffee ice cream. In other words, there are different versions of ice cream. There are different flavors of ice cream. The idea of multiple mass numbers for an element like carbon tells you that there are multiple versions of carbon atoms. Yes, all carbon atoms are the same because all carbon atoms have the same number of protons in their nucleus. All carbon atoms have the same number, have the same atomic number, but you can have slightly different variations in the number of neutrons, which is why you can have different flavors, different versions, different types of the same atom. Okay, okay. All ice cream is the same, except we have different flavors of ice cream. Okay. All right. So let's see here. I have another question for you. All right. Let's go back to Israel. Israel, I'm going to ask you a question that you don't necessarily need your textbook for. Okay. So Israel, please say hi to us again.
Hello.
Hi, Israel. So Israel, did you happen to get your textbook up?
Yeah, I have it actually up on page 32.
Okay, great. Okay. So Israel, here's my question to you. If I'm holding a carbon atom with a mass number equal to 13 in my hand, if I'm holding a carbon atom with a mass number of 13 in my hand, can you tell me how many neutrons are present in the nucleus of that atom?
Mm. It'd be like 6.
You're close, but that's not quite right. You want to reconsider?
And that's really all I have.
Okay, thank you, Israel, for attempting. I do appreciate it.
Yep.
All right. So let's open it up to the broader audience. If you think you know the answer to my question, please put it into the chat window. Again, the question is this: if I have a carbon atom with a mass number of 13 in my hand, how many neutrons are present in the nucleus of that atom? Okay, so I'm seeing some of you put in an answer of 7, and that would be correct. So I'm just going to take a pick here. So let me see. So Noah Miranda. Noah, could you please say hi to us?
Hello.
Hi, Noah.
Hi.
Noah, could you please explain to your classmates how you actually arrived at the number 7 for the answer to this question?
Sure. So basically, we take the mass number minus the atomic number, because that will tell you, because the amount of protons in an atom doesn't change, but the amount of neutrons can change. So you take the mass number minus the atomic number, and that should tell you how many neutrons are available at your disposal.
Okay, great job, Noah. You're exactly right. In other words, just to restate what Noah was saying, right? If you take the mass number, which is the total number of protons plus neutrons, and you subtract the atomic number, which is the known number of protons, what you're going to be left with is an answer that tells you the number of neutrons, right? So to get the answer to this, all you had to do is take 13 minus 6, and you would end up with 7 neutrons, okay? Folks, this is the kind of reasoning that I would expect of you on an exam, where I present you with information. You know, I might have a data table or something like this, and I ask questions like this, where you just have to do a little bit of deductive reasoning, apply a little bit of logical thinking to the information that's in front of you. So my point of this is that as you see the answer here, hopefully you don't think this, you know, this isn't hard, but you don't want to psych yourself out. You don't want to start getting all these vocabularies and think, oh my God, isotopes, atomic number, mass number, neutrons, protons, electrons, what am I supposed to do, right? Just slow down and think about what the question is asking, and then it becomes pretty reasonable, right? 13 is the mass number of the atom that we've stated. That's the number of protons plus neutrons. So if I know the number of protons, I can subtract those two values and come up with the number of neutrons. In this case, it's 13 minus 6 equals 7 neutrons. Okay. All right. So I will point out that, so let me just pause. Do you have any questions right now? All right, please let me know if you do. Okay, so, mass number and atomic mass are very similar. But again, please have in your mind that mass number is talking about the protons and neutrons in a single atom, whereas atomic mass is talking about the average number of protons plus neutrons in a group of atoms. This explains why the atomic mass of chlorine is 35.45, okay? Right, so an example here, the atomic mass of chlorine is 35.45. Notice that this number is not an integer. Okay. In an analogy, right? Within an analogy, you might hear a politician say that the average number of people in an American family is 5. Okay. But your family might have 4 people and somebody else's family might have 6 people, right? So if we average them together, we could get 5. Okay. If we averaged, a family of 4 together with a family of 5, that would be 4 plus 5 is 9. 9 divided by 2 is 4.5. Right? So by using averages, we can get numbers that are in fact not integers. Okay. All right. Any questions at this time? All right. So we've defined some characteristics of atoms: atomic number, mass number, and groups of atoms, which would be the atomic mass statement. Let's see here. So Israel is asking me in the chat window where notes are posted. Israel, notes will be posted in the lecture portion of Wiley Plus under the Files tab. Under the Files tab within the lecture portion of Wiley Plus is where notes are put. Okay, so all right, let's see what else here. I want to talk a little bit more about these isotope beasties, okay? In other words, I want to talk about what the clinical relevance of isotopes is, okay? Okay. Now, of course, this is school and we're doing a chapter on chemistry, so we expect you to know something about some basic principles and properties of chemistry. You're not going to be an expert from this one chapter. I mean, let's forget that, right? I mean, you need a couple years of dedicated chemistry training to become an expert. But there's certain basic principles we can try to get you to appreciate. Isotopes, which now we've stated up here for you, right? Isotopes are atoms that have the same atomic number, but have different numbers of neutrons present in their nuclei. That's nice for class, Dr. Allen, but why should I care about that as a future nurse or doctor or radiation technologist or whatever I'm going to be? Why should I care? Okay. The reality of it is that isotopes are clinically useful in the hospital. Isotopes are used for a number of things, but let me just give you one example. Okay. Isotopes are frequently used to locate the presence of diseased tissue in the body, particularly tumors and cancer tissue. Isotopes are useful to identify disease tissue in the body where the disease tissue is. Okay, I mean, you might go into your doctor with symptoms, with unexplainable symptoms, and the doctor says, well, we better need to do some testing to see if we can locate any tumor in your body, okay, or something like this. And so let's talk about this, okay? All right, you know from our conversation already today, this morning, we put it in your notes that there are two mass numbers for carbon, right? We've already stated that, right? There are two isotopes of carbon listed in your textbook. That's figure 2.2. And the two mass numbers are 12 or 13. Okay, so let me just ask a question here. Okay, let's see. Is Morgan Bruni with us today? Morgan, could you say hi? All right, I guess Morgan's not online with us today. Okay, let's try Jordan Benson. Jordan, can you please say hi?
Hi, Dr. Allen. My name's coming up as my brother's again, but it is me.
Okay, thank you. So Jordan, do you have your textbook open?
Yes.
Okay, so Jordan, when you look at figure 2.2 and you look at the mass numbers of 12 or 13, it looks like one of those two numbers is printed in a boldface font. Which number is in boldface?
12.
12. Okay, so Jordan, what does that tell us?
That it's the most common isotope.
All right, beautifully stated. Thank you, Jordan. Appreciate that. Okay.
Yep.
All right, so the carbon 12 isotope of carbon atoms is the most common version of carbon. Okay, and let me say this: of all the molecules in your body that are built from carbon atoms, 99.9999999% of them are made of carbon 12 atoms, not carbon 13. Okay. 99.99999. I'm going to exaggeration extremes, right? Almost 100% of all molecules in your body made of carbon atoms are built from carbon 12 atoms. Okay. All right. So we're just telling you some factoids that are going to allow us to present a story here that shows you the clinical relevance of isotopes. All right. So let's switch gears at this time. Was there a question?
Yeah,
Go ahead.
can you hear me?
Yes, Scarlett.
Okay, I just was wondering, so then if most of them are built from carbon 12 atoms, then which ones are the ones built by 13? Like, is it like one or two specific ones?
Okay, that's a nice question, and let me say this: it would be basically impossible for us to identify the very, 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 very tiny percentage of molecules that might happen to have a carbon 13 atom. In other words, the carbon 13 atoms are so rarely present in our molecules at such random locations that we would have a hard time even identifying any place where we find them. Does that make sense?
Okay, thank you. Yeah.
All right. So let me see if I can help with your perhaps discomfort with that idea, Scarlett, with continuing with the story here. And so, okay, so I want to talk to you about cancer, okay? And now I don't want to get into a big conversation about cancer, but let's put a question down, okay? All of the talking points under the heading of clinical relevance of isotopes is leading to a punchline. Like I'm telling you a sick joke, I'm leading to a punchline here, okay? So question, what properties are associated with cancer cells and tissues? There's lots of things that cancer does, but I'm fishing for one particular property. When you think about cancer, what are the cancer cells? What are the cancer tissues? What are some of their characteristics or properties? Okay, so Raquel mentions mutation. That's certainly true. That's a nice response. Noah says unfettered growth. Okay, so I'm going to take Noah's statement and run with this. Okay, Israel, they mutate. They like to grow fast. That's true. Okay, so for everybody, if a cancer cell is going to grow fast, if it's going to grow fast, if it's going to have unfettered growth using the language of Noah, does that suggest to you, give me a thumbs up or a thumbs down or some kind of response, does that suggest to you that cancer cells probably are burning through a lot of resources? If a cancer cell wants to grow and reproduce, does it make sense that the cancer is burning a lot of resources? Hopefully you can see that that is true. And so that what I'm fishing for here to help make a point is that cancer cells have a very accelerated or aggressive metabolism. They have an enhanced, rapid, fast metabolism. Okay, so they have an elevated metabolism. The majority of molecules you consume in your food and the energy from those molecules will be used by cancer cells to drive the growth and reproduction of the cancer. Okay, in a very rough but not quite accurate analogy, if you ate a cheeseburger, then you might imagine in our talking conversation right now, if you ate a cheeseburger, that maybe 85% of the molecules and energy content of the cheeseburger are consumed by the cancer in order to support the cancer's growth and reproduction. So most of the material from the food you eat supports the life of the cancer cells. So here's where I'm heading. If we want to identify where a cancer or tumor is in your body, if I feed you a normal hamburger, which is made from meat from an animal, that meat from an animal is made of molecules that themselves have carbon atoms, and the carbon atoms in the meat of the molecules, of the meat, are carbon-12 atoms. I would have no way to tell apart the carbon-12 atoms of the hamburger that I've eaten from the carbon-12 atoms that are naturally found in most of your body. Okay, I'd have no way to tell it apart. So the way isotopes come into the picture is this, okay? A rare isotope of an atom, in this case, carbon-13. A rare isotope of an atom is, through means that we're not going to explain to you right now, spiked into something that a patient would eat or consume. Now, you could spike carbon-13 into eggs. You could spike carbon-13 into sort of a milkshake kind of concoction that a patient would drink. Okay, and the point of it is that you're asking the patient to drink or eat a quote unquote food that is spiked into that material. So in this case, carbon-13 is spiked into a digestible food that a cancer patient will eat. Okay. So what I'm saying to you is that your body is predominantly made of molecules that are made of carbon-12 atoms. I need a way of locating where a tumor is. A tumor is made of carbon-12 atoms. But a tumor has an aggressive metabolism. So when you eat something, most of the molecules from your food are going to go into that tumor tissue. The trouble is I need to be able to separate and identify the carbon-12 of the tumor from the surrounding tissue, which is not possible. So how do we do this? We feed the patient a different version of carbon, an isotope of carbon, a rare version of carbon. In this case, carbon-13, which is not normally found in the body in high amounts. That carbon-13 will be taken up predominantly by the cancer tissue And because carbon-13 is different than carbon-12, if I have the right equipment, the right fancy technology, I can actually locate where the majority of carbon-13 that you ingested in the food is localized in your body. In other words, we use an isotope to detect the diseased tissue. Okay. I'm gonna type this out into the notes, but let me ask you a question in the chat window. Am I making sense here? By having a patient ingest a different form of carbon, okay, carbon-13, not normally found in the body, with the help of special equipment, a doctor can locate where the majority of carbon-13 was used. Since cancer uses the majority of material from foods you eat, most of the carbon-13 will go to the tumor. Okay. So in this way, we can actually use isotopes to diagnose where your kidney tumor might be, where your bone tumor might be, where your brain tumor might be. We can locate where it is and how big it is. And then we can start to develop strategies to try to attack it and kill it to save your life. Okay. All right. Folks, do you have any questions right now?
I have a question. So I don't know if I'm thinking too much into this, but if the tumor would be using the energy from those molecules, wouldn't it be like an influx of ATP at that site, or like the form of energy that it's using rather than the carbon-13?
So Raquel, it's nice that you know about ATP. It would not be an influx of ATP literally like you're thinking, but what is going to happen is the cancer cells will eat the carbon-13 food, and in the process of breaking the carbon-13 food down, ATP will be manufactured. So you're not eating ATP, you're eating food that allows the cancer cells to manufacture ATP.
Okay, so then at this, like at the site where the tumor is, the carbon-13 from the food would then be processed into ATP, and you can see that at the tumor location. Okay, now I get it.
Yes, in very rough generalized language, without going into details, the answer is yes to your question.
All right, thank you.
I have a question.
Go ahead, Scarlett.
Well, I guess a statement. All right, so from my understanding, so isotopes you said are used to like figure out diseases in tissue. And when I had asked that question about like the 13 isotopes and the carbon-13, like you were just explaining that like the carbon-13 are usually like the cancerous cells, because, or no, am I not understanding right?
So let me see if I can clarify, Scarlett. So the cancer tissue in your body the cancer tissue in your body will be abnormal cells that are also made of carbon-12. What I need to do is get the cancer tissue to take up a substance that is made with a different version of carbon, so equipment can detect that different version of carbon to locate the cancer.
Oh, okay. Now I understand. Thank you.
Sure thing. So Israel has a question. Isn't the food we eat toxic then if it helps cancer cells grow? Yes, in a way of thinking it would be toxic, Israel, but the reality of it is if you don't feed yourself, the healthy cells in your body will also die. So you have no choice but to eat. I mean, you got to eat. Unfortunately, when you eat, you are going to fuel the cancer, which is why we need to find good medications and treatments to attack the cancer and kill it. easier said than done, obviously. Okay, other questions? Okay, all right. Okay, folks, hang in there. We're going to keep rolling. Okay, I think at this point, I've tickled you enough with atoms and atomic characteristics enough that I'm going to start moving to a different topic, which is chemical bonds. Chemical bonds. Okay, so let's start talking about chemical bonds. All right. Chemical bonds are talked about on pages 34, 35, 36, 37 of your textbook. 34, 35, 36, and 37 of your textbook. Okay, so I don't know how much you know about bonds or how much you've read here so far, but let me just make a few starting statements here. When we talk about a chemical bond, we're talking about a type of attraction between atoms. Okay, so we are currently on pages 34 and 35. Pages 34 and 35. So chemical bonds are really invisible forces of attraction between atoms that hold atoms together to form molecules, right? If you think about a very simple molecule, H2O, 2 atoms of hydrogen and an atom of oxygen, these 3 atoms are held together in close proximity by each other by this invisible attractive forces called chemical bonds. Okay. Now, even today, we're still trying to figure out what the essence of this attractive force is. It's kind of like trying to define the word love, right? We could all define love slightly differently, and that they might be roughly equivalent, but not necessarily equal, right? We're still trying to figure out exactly what is this invisible force. We know that it's there, we can measure it, but what really is it? I mean, that's a hard thing to describe. Okay, so let's continue here. There are 3 major types of covalent bonds that are talked about in your textbook. If you've had a proper chemistry course, you know that there are actually a couple other varieties of chemical bonds. There are things known as van der Waals interactions and hydrophobic forces. These are things that we're not going to focus on in our course, but we'll just stay to the meat of what is printed in your textbook, okay? So there are 3 major types of bonds listed in your textbook. They are ionic bond, covalent bond, hydrogen bond, okay? And I'm going to talk about each type of bond, but I want to offer you a way to think about what a bond is, okay? When you read your book, and particularly if this is the first time you've been thinking about chemical bonds in a very long time, now as you read the book, you might think, okay, well, we got 3 different types of bonds. In other words, ionic, covalent, and hydrogen are actually different from each other. And while they are different from each other, I want you to focus on how they are similar to each other, okay? While the 3 types of chemical bonds are different, they actually are very similar too. All right. So, in other words, I want you to focus on the similarity here as a way of thinking about the bonds rather than the differences. And it's kind of a subtle point, but hopefully I will make sense here. All right, so I have an analogy that I want you to think about. And my analogy involves a triangle. Okay, so forgive me for a second, but I'm going to do a little bit of drawing on your screen here. I do have a digital pen at my desk here. And so let me draw a triangle. Okay, let me draw a triangle. Okay, so there is a triangle, perhaps not a beautiful triangle, but it is nonetheless a triangle. So here's my question to you in the chat window. Here's my question to you in the chat window. Okay. Let me get this typed. Here we go. If I point to any edge of the triangle, left, right, or bottom, am I still referring to the same triangle? In other words, as you consider your response to that question, if I draw an arrow to the left edge or to the right edge or to the bottom edge, am I still pointing to the same triangle? I hope you can get comfortable with the idea that, yes, I am pointing to the same triangle, okay? That's how you should think of your chemical bonds. They are different edges of the same phenomenon. They are different edges of the same object. They are different edges of the same talking point that we can talk about to consider what bonds really are. So drawn in no particular order, I could have ionic here on the left, covalent on the right, and hydrogen bond on the bottom. Again, not drawn in any particular sequence or order. And all of these bonds are like three edges of the same triangle, okay? So, I want you to think that, yes, bonds are different, but they also have a great deal of similarity. So let's talk about this. And so, hold on a sec, I need to turn my drawing off. Okay, and I'm going to hold up here. Insert. Oh dear, I think I went crazy here. What did I just do? What did it do? Oh, it did that. Okay. All right, I'll fix my notes later and make them pretty for you. Let's see if I can. Technology is great, except when it just gets in the way. Okay, so I'll come back and make that pretty later on. Okay. So once again, the notes, okay, I keep getting asked this. So the notes will be posted on Wiley Plus in the lecture portion of Wiley Plus underneath the Files tab, okay? All right, so let me continue here. I will fix the ugliness of these notes and put them up later on. Okay, so let's just start here. Okay, here's a question, okay? In what manner are the three types of chemical bonds the same? Here's the manner that they are the same. All chemical bonds are concerned with an attraction between oppositely charged particles. All chemical bonds are concerned with an attraction between oppositely charged particles. Now, what are those oppositely charged particles? You already know them, right? They're the protons and the electrons. Okay, so all chemical bonds, whether it's ionic, covalent, or hydrogen, are concerned with an attraction between oppositely charged particles. So the next question is, in what manner are the three bonds different? And the answer here is that while all the bonds are concerned with an attraction between oppositely charged particles, where we get the difference, where we get the reference to a different edge of the same triangle, is that the different bonds are concerned with different amounts, different magnitudes of attraction between oppositely charged particles, okay? Each type of bond is distinguished from each other according to the magnitude of attraction between oppositely charged particles, okay? So think about it this way, and I'm going to put this into the chat window here. Okay. Okay, hold on a second. Here we go. One more time. Here we go. What is the common idea between these words? Pudgy, overweight, obese. What is the common idea between these words? Pudgy, overweight, obese. Okay. So I'm seeing a lot of folks state the word fat. Okay. And so fat, overweight. Okay. So you're approaching the idea. You're approaching the idea. But let me ask you this. Let me ask you this in the chat window. Okay. Okay. Would pudgy and obese really be interchangeable? Would you apply the same word to a single person? Pudgy and obese. Would you really use those two terms for the same person? Okay. I hope you wouldn't, right? I hope you wouldn't. So what's the common idea here? Do you see that the common idea is these words, pudgy, overweight, obese, generally refer to carrying an excessive amount of body weight, but just how much excessive body weight is a person carrying? If a person is carrying a little bit too much body weight, you might say pudgy. If a person is carrying a very unhealthy amount of excessive body weight, then you would use the word obese. Okay, so these words are all talking about carrying too much body weight, but each word has a slightly different meaning in terms of how much or what the magnitude of excessive body weight really is. That's the same thing for the chemical bonds. Ionic covalent hydrogen, all talking about an attraction between oppositely charged particles, but just how strong is that attraction between oppositely charged particles? Okay, folks, are you okay right now? Any questions? All right, so what I'm going to do next is put into your notes a table that talks about some of the things we've been describing. Okay, Shri, I see your comment to me. I understand. Let me insert a table here. And we're going to use this to categorize our bonds. Okay, bond overview. All right, so we're going to put here type of bond, We're going to put here the strength of the bond. We're going to put here the length of the bond. When I say bond length, I'm talking about what is the length, like if you could measure with a ruler, what would be the distance between the atoms that are joined by a bond? What would the distance between the atoms joined by a bond actually be? Okay, and I'm not going to put numbers on this, although we certainly could, but let's see. The bonds are ionic, covalent, and hydrogen. All right. So question in the chat window, okay. Which type of chemical bond is the strongest? Which type of chemical bond tends to keep its atoms held together very tightly, the most tightly? Is it covalent, hydrogen, ionic? What say you? Okay, I really appreciate folks that are participating. Remember, I want you to participate. Don't be shy to participate. Don't be afraid to be wrong. We're all here to learn, okay? So if you look at the community of responses, you see there's considerable differences in responses. The correct answer to my question, the strongest type of bond is covalent. Okay, covalent is the strongest type of bond. All right. The weakest type of bond is actually hydrogen. And the bond with the middle amount of strength is the ionic bond. Now, you may not understand why this is true yet, and that's okay, because we're in this conversation. We're just getting started here, okay? But I'm telling you that a covalent bond is stronger on average than an ionic bond, which on average is stronger than a hydrogen bond, okay? This is how the bond strengths are rated and related to each other. We'll get into why they are that way in the next minutes and in our next conversation next Monday, okay? So the bond length, okay, let me ask you in the chat window. Which bond has the shortest length? Okay, which bond has the shortest length? Okay, got one response. How about the rest of you? Okay, I think maybe I've made you shy. Okay, again, don't be afraid to be wrong. Just do your best. Okay, so right, the bond with the shortest length corresponds to the bond with the strongest strength. Okay, so this is covalent. Covalent has the shortest bond length. Hydrogen has the longest bond length. And ionic is always the middle guy, the middle child of the family, okay? All right, so let's think about this a little bit to develop some intuition. Why is it, and why did I type hydrogen down there? That made no sense. Okay. Why is it that a hydrogen bond has the longest length? Well, think about it. If a hydrogen bond is the weakest bond, let's say that my two hands that I'm showing you, my left and right fists here, are atoms, and that they're connected with a hydrogen bond. That means there's not a lot of attractive force between the atoms, so the atoms are not going to be pulled very close together because the attraction is very weak. So they're not going to be pulled closer together, which means they're going to stay further apart, which means you're going to create the longest bond length. In a very rough, similar analogy, think about a dating relationship. Think about the last time you had a dating relationship. Is it easier to date somebody that lives in your geographic area or to have a long distance relationship with somebody in another state? I mean, I think we can appreciate that maintaining a healthy relationship with somebody who's physically distant from us is very challenging, which means the strength of the bond is pretty weak. A lot of long distance relationships don't work out. Okay. All right. Thoughts, questions? Okay, let's keep going, folks. We have about 5 more minutes to get another topic started. Hey, what the heck? Yeah. Okay, I will take care of the ugliness of the notes when I'm off screen with you guys. Okay. So next topic, we are talking about chemical bonds. So what we need to do now is actually define the chemical bonds. Okay. Bond definitions. Okay. Here we go. Ionic bond first. Okay, an ionic bond is shown to you on figure 2.4. Figure 2.4, page 34. Okay. An ionic bond is an attraction created between atoms when one atom donates one or more pairs of electrons to a neighboring, when one atom donates one or more electrons, not pairs of electrons, when one atom donates one or more electrons to a neighboring atom. The example that your book and most beginning textbooks use for this, and it's a perfectly good example, it's just that I get tired of talking about it because I teach it so much, is the sodium chloride example. That's what figure 2.4 is explaining to you. So let's talk about sodium chloride. Okay, sodium chloride is table salt, right? That's table salt. So you had some salt in the food that you ate this morning for breakfast. If you had a cereal, they are, the cereal is loaded with salt. So let's talk about what this is. Okay, so sodium chloride, this is a molecule which happens to also be a compound, because a compound is a molecule that is made of at least 2 different types of atoms. And you can see here we do have 2 different types of atoms. We have sodium and we have chlorine. Okay, so sodium chloride is a molecule. It happens to also be a compound because we have 2 different types of atoms present. Okay, so what we need to do is try to explain to you why sodium and chlorine atoms come together to form this molecule in the first place. What is the circumstance that causes these atoms to be attracted to each other? Okay, I don't know that I can finish this today, but I'll take my time and get it started here. Okay, so I'm going to draw a bit more. All right, and so let's say that we have sodium and chlorine. And notice that I've drawn them apart from each other. I've intentionally separated them with a little bit of difference to let you know that I'm implying that right now in the conversation, I have a sodium atom and a chlorine atom, and they are not bonded. They are not together. Okay, so, all right. Okay. I'm basically at 9:15 here, and I don't want to start a heavy concept and just have to chop it up. So I'm going to pause here. Okay, I'm going to pause here. Folks, do you have any questions at this moment? Okay, we do have lab this morning. So, I do like to take a little bit of a nice break since lab can be long. So let's take an extra 5 minutes. Let's start lab this morning at 9:35. The Zoom link will stay open. It will stay active. So you can stay logged in. That's not a problem. And I will see you at 9:35 for lab. Okay, so I'll see you in about 20 minutes. Take a nice break.